So this is the example. It says a slurry composed of 250 ton of water, 10 ton of dissolved potassium chloride and 60 ton of solid potassium chloride at 80 degrees centigrade and 4 bar has to be passed through 30 number of hydrocyclones, each having 200 millimeter diameter. The feed particle size distribution is provided. So you have to simulate the process using user-specified ratio type and user-specified efficiency. Now I have shown you an Excel file where user-specified efficiency has been given. In the same Excel file, user-specified ratio type also has been given, and I will provide those dimensions. So with those dimensions, we have to simulate that process. And then we have to simulate again the same process using Ritema rectangular type, okay, with user specified efficiency and Ritema rectangular type. So we shall change the type, not the efficiency. And then in the third problem, we will use the pleat efficiency and in design mode. So we will change the efficiency as well as the mode. So from simulation, we'll go to the design mode. And for design mode, our maximum allowable cylinder diameter will be 250 millimeter and the pressure drop will be 50 kilopascal. Okay, so let us solve the problem. So for that, let us go to the properties first. We have to provide KCl. So here you will find there are two types of KCl. One is dissolved KCl and solid KCl particles. Okay, so let us rename them as KCl-S and we shall make it solid. And we will provide KCl once again and water. So this is solid KCl, this is conventional KCl that can be dissolved, and this is water. Okay, and we can press next, use solid, run the simulation. Okay, now let us go to the simulation. In the flow sheet, we have to provide the feed stream, and before going to the feed stream, we have to specify the stream class, and the stream class has to be the mixed CLPSD. Okay, now nothing has been said about the particle size distribution over here in the problem. Rather, it is said that we have to use the user specified ratio type and user specified efficiency. So when we see user specified efficiency, we will get some information from Excel file. So let us go to the Excel file and let us see what information we can get. So this is the feed particle size distribution. It is from 0 to 1.25, 1.25 to 2.5, 2.5 to 3.75 to 25. So there are 20 divisions and all of them are equidistant. So let us take 20 division with equidistant from 0 to 25. Yeah, 0 to 25, 20 divisions, right? So 0 to 25, 20 divisions. Okay, so create PSD mesh. So we have 0 to 1.5, 1.25, 1.25 to 2.5, 2.5 to 3.75, up to 25. Okay, 20 intervals we have got. And stream class already we have set to mixed CL-PSD. Now go to the input. Input, it is 80 degrees centigrade, 4 bar pressure. So 80 degrees centigrade and 4 bar pressure. Then we have 250 tons per hour water. So it is 250 and 10 tons per hour of KCl. So KCl is 10 tons per hour. And then go to the solid. Solid also 80 and 4 bar. 80 degrees centigrade, 4 bar. And mass flow tons per hour. It should be 60 tons. So it is 60 tons. Now particle size distribution we have to fix, and this is user specified value, right? Now user specified, we have to provide the weight fraction. So simply we go over here, copy these weight fractions, and we fix it over here. Okay. So we have given the weight fraction. Okay. So our feed is completely defined. Now we have to specify the inlet specification of the hydrocyclone. What is the first case? First case is the simulation of the hydrocyclone with user specified ratio type and user specified efficiency. So both of them are user specified. This is user specified ratio. And we have to provide the value of the diameter of hydrocyclone is 200 millimeter and 30 numbers of them. So it is 200 millimeter and 30 numbers of such hydrocyclones. Parameter for liquid flow split model and other things are already given default values, so we are not disturbing those values. Let them be like this. We have to provide the efficiency. So efficiency, we have to simply provide the solid particle diameter and the efficiency. Again, we go to the Excel file, the solid particle diameter and efficiency are given. Only thing is that we have to change it to micron and the efficiency has to be from 0 to 1. So what we will do, we will copy this portion. So these are in micron. So we shall put this in micron and paste it. Okay, so we have put the values of solid particle diameter. Now we have to provide the efficiency as well, but the efficiency has to be from 0 to 1. So we have to make it B2 by 100. So that is okay. So this we can copy and we can paste. Okay. So we have given the values over here. Okay. So we have given those values 0.245 to 1. So we have fixed the efficiency. Now we have to provide the ratio. Now let us see. Again, go to the Excel file. And here the dimensions of the hydrocyclone has been given. Now this is the diameter of the cyclone. So ratio should be 1. Length of the cylinder is 300 millimeter. So it is 300 by 200. It should be 1.5. Diameter of the overflow is 48. So 48 by 200 it is 0.24. And like this, all of them has to be given. And cone angle is 20 degrees. So it is a rectangular type of inlet. So height and width have been given. So it is not round shaped. So this information we have to provide over there. So let us give them one by one. So length of cylinder, it is 1.5. So give 1.5. Diameter of the overflow, it is 0.24. So give 0.24 instead. So these are the default values given over here. So we can change them. Diameter of underflow, it is 0.15. It is 0.15 over here. Height of inlet and width of inlet. So they are 0.24 and 0.16. So we give over here 0.24 and 0.16. Cone angle 20 degree, it is by default is given. Okay, we can use it. So that's how all other parameters have been fixed. Now we can run the simulation. So run the simulation. Okay, so results are available. So let us analyze the result. So for that, we'll go to the stream results first. So in the stream result, you will see the mass flow, let us convert into tons per hour. Okay. So 60 tons per hour of solid KCl was fed, out of which 42.82 tons per hour is going through the solid outlet, that is underflow, and 17 has been pushed through the overflow as a liquid. Most of the water is going through the liquid and some of the water is coming through the underflow. So although the separation is not very good, but the efficiency curve that we have got, this is the best result we can get. Now we can see the particle size distribution. In the particle size distribution, you see the feed. So above 2.5 micron, almost everything has gone towards the solid outlet. Very few is going to the liquid. On the other hand, the finer particles, that is 0 to 1.25, that is going through the liquid outlet or overflow, and very few amount they are going through the underflow. But obviously some will go to the underflow because of the fish hook effect. Now we see the other results. What is the pressure drop? Pressure drop in terms of kilopascal, it is 44 kilopascal. So if you remember the operating range, the pressure drop between 35 to 345 kilopascal operating range is acceptable. And we are getting the pressure drop to be 44 kilopascal. So it is within the acceptable operating range. But the overall separation efficiency is 71%. So this overall separation efficiency of 0.713781 may be cross-checked with this value. Here it is this by this, so it is 42.8268 by 60. So if you calculate, you will find 0.713 whatever separation efficiency is being shown over there. So you can calculate, you will get this one. And the volumetric flow rate of overflow, volumetric flow rate of underflow, they have been given. And the height of inlet, width of inlet, all of them are given. The inlet liquid velocity is 6.34 meter per second. So you can think of what is the magnitude of this velocity. And this one is a conversion of separation efficiency to corrected efficiency for the particle diameters in micron. The equations for corrected efficiency already you have learned. Okay, now we go to the next problem. We have to change the user specified ratio type to Ritema rectangular type. So we will keep the efficiency correlation as it is, but the type we will change to Ritema rectangular. Okay. So we do not have to give any more information. Obviously, ratio will be again deactivated because we are not using our own ratios, that user specified ratios rather. Let us run the simulation and see the differences. Now, okay, we have run the simulation. Go to the stream result. Now, if you see the results tones per hour, you don't see any difference because the separation efficiency will be same as before because separation efficiency curve has not changed. We are using the same efficiency curve that we have changed earlier. So these values are not changing. Let us see the particle size distribution, whether there is any change over there. No, there is no change over there at all. Obviously, the particle size distribution is also related to the separation efficiency, so they will not change. But other results, we can expect some change. For instance, the inlet liquid velocity is 0.989079. Okay, so why it is changing? Because the dimension of the hydrocyclone is changing. For instance, you see the dimension of height of inlet, width of inlet, length of the cylinder, overflow, and underflow diameters. And you can compare with our values that we have used as a user specified ratio. So these are the two things that we can compare. For instance, the length of the cylinder. In our case, it was 300 millimeter, but they are using length of cylinder 591, quite high. Then diameter of overflow, our case it is 48, but for them it is 68. Underflow diameter, our case 30, theirs is 40. Then inlet, we have used 48 and 38, they are using 85 and 28. So their dimensions are quite big. And as their inlet opening is larger, so inlet liquid velocity is also reducing. For our case, it was, if you remember, it was 6 point something, but in this case, it has reduced to less than 1. Okay, so that is the effect of type. Okay, now we shall change it to design mode, and efficiency we will use split efficiency rather than our user specified type, and we have to repeat the exercise. So we will use split efficiency, leave it as Ritema rectangular, and keep it design mode. Okay. Now, nothing has been said about these parameters of F1, F2, F3, F4. So, as nothing has been said, we will keep it there because we do not have any idea of those parameters. So, let us keep them as 1, 1, 1, 1. And fish hook model K and KB, they are not given. So, let us assume that there is no fish hook model. There is no fish hook effect for this process. But we have to provide a couple of new information, that is the design parameters, which are maximum diameter and design pressure drop. If you remember, in the earlier case, our pressure drop calculated was around 44 kilopascal, right? But in this problem, they say that maximum allowable cylinder diameter is 250 millimeters. So we can have a higher diameter cylinder, that is 250 millimeter, and we can go up to 50 kilopascal pressure drop. So our allowable pressure limit is higher. So let us use a 250 millimeter diameter hydrocyclone, and pressure drop we can choose 50 kilopascal as per our design problem. Okay, and run our simulation. And now check the result. Now see, now we are using pleat efficiency. If you go at the top, the efficiency has been changed. So our new efficiency is 72%. So efficiency has not changed much. The pressure drop, as we have fixed it to be 50 kilopascal. So 50 kilopascal is there. But there has been some change in the height of inlet. Height of inlet is now 103 millimeter. Width of inlet is 34. Cylinder length has to be increased. Yeah, it has increased to 655. Earlier it was 591 or something. Overflow and underflow, they are also increased. The length of vortex is 96 millimeter. And see the diameter of the cylinder. We have said that maximum diameter allowable is 250 millimeter. So they have optimized and they are suggesting us to use a diameter of 240.1 millimeter. And with that, they are saying that number of cyclone needed is 8. So in the simulation mode, we are using 30 such hydrocyclones. But here they are saying, why are you using 30 cyclones? Only 8 cyclones will be sufficient for our separation. So that is the advantage of design. So they are not only designing the dimensions of the hydrocyclone, but they are also giving you the number of such hydrocyclone which need to be used in this case. So with that, we come to the end of this lecture. I hope you have enjoyed it, and we will come back with yet another interesting lecture very soon. Thank you.